Okay. Hi. Hello. How are you? I'm fine. Thank you. Oh, very good. Our relationship is getting improved. I'm glad. Any questions from the last lecture? So I guess we finished all the classical aspects here, right? We talked about the gamma matrices. We talked about all spinor bilinears, which are 16 components, which are the basis for all fermion bilinears according to the tensorial geometry, right? And then we talked about some of the identities. And then the last thing we talked about, I believe, are two projectors, right? Two projection operators. So regardless of the representation, meaning either you use a Weil basis where four components are nicely divided by left versus right, or you can use a Dirac representation where things are now divided into particle, which has both left and right, and an antiparticle, which also has a left and right. We talked about two projection operators, otherwise known as complete relation for spinors. Yes, sir.
I have a question then. Why there isn't gamma 5 in all the dimensions?
Dimensions? Yeah. Well, you already have that. So, for instance, if you go to the 5 dimension, gamma 5 is a part of already gamma matrices. So your question is, why can you not define gamma 6? Is that your question?
Yeah, I wonder why gamma 5 is related to the other gamma matrices in the dimension, or like even.
Okay, let's be specific. So suppose we talk to 5 dimensions. Okay, so then we will have to look at the Clifford algebra in 5 dimensions, which already has a 5 gamma matrices, because I'm in the 5 dimension. So gamma, so in 5D, what happened here? Was there a battle here or something? Okay. So for instance, 5D, as an example, we will have like gamma A, gamma B, which is 2 matrix AB, and then identity matrix. Okay? I haven't specified the dimension of this yet, meaning like whether I'm looking at the 4-dimensional, 6-dimensional representation. I haven't specified it yet. But in 5D, for instance, A and B, I have all 5 times. Suppose I'm in the Euclidean space. Okay. So, okay, so I'm in there. And then your question is?
Okay, what? Is there gamma 6?
Okay, so good. So that is related to somewhat mathematical, but eventually very physical question about the representation theory for Clifford algebra. Okay, and as we talked about, for instance, going back to 40, in addition to gamma mu, which has 0, 1, 2, 3, we define this stuff, right? Which was I over factorial, epsilon, mu over sigma, gamma mu. You know what I'm talking about, okay? So eventually, the deep reason is that given this matrix and with a specification of dimension, which I can write down universal equation, right? This equation takes the exact same for regardless of the dimension of the space and time, right? It's just go from 1 to b dimensions. So then, really, the question was in 4D, for instance, we talked about 4-dimensional representation, which was the 4-component representation. And then, if I run the argument backward, the existence of such an object called the gamma 5, for instance, happened to be that we found that in addition to the 4-dimensional representation, which had 4x4 matrices structure, 4x4 matrices, this allowed us to actually learn that we actually have a projection onto a smaller dimensional representation. And I told you that because of this, I can actually divide 4-dimensional Dirac into literally left versus right 2-dimensional representations. In fact, in the Weil basis, it was clear because the gamma mu is a sigma mu, sigma bar mu, like so. And then one can check that sigma bar, in fact, satisfies Clifford algebra on its own. What that means is that the existence, in this case, what's known as the chiral gamma matrices, is linked to the fact that in 4D, the minimal dimensional representation of the Clifford algebra is not 4-dimensional. It is actually a 2-dimensional representation, which is linked through this relationship, because this is how we divide that into 2 pieces. 5D, just give you a quick answer, the minimal dimensional representation is a 4-dimensional representation. So the smallest object one can talk about in 5D, for instance, the Rock spinner, not the Bob spinner. And that is obviously linked to the fact that there's no such a thing, projection operator. So I guess you can go and learn and think about 2 different ways. One, just check what happens if you try to write down this object. Okay, I'm gonna do it, right? Just multiply 5 different objects. This is gamma 1 to the gamma 5. Okay, and check. I mean, for instance, this has 4 of them. You can check what property this has. And then you can check whether this has a desired property as a projection operator if you try to do it. Okay, if you try to do it. And then you should find that A, such an object is trivially 0 or 1, so that's nothing useful. B, even if you can construct somehow which is not equal to 0 or 1, then if you try to do this job to see whether, given a 4-dimensional representation or 6-dimensional representation, whether you can try to divide that eigenspace into the smaller eigenspace, meaning there is no projection operator. So then you will fail in 5D, for instance, in 3D that you can do that. So overall, what that means is that in D dimensions, when you try to find a representation for Clifford algebra, right? Given an n set of that, and so D set of that, okay. To me, the best place to look at is the Polchanski string theory book. There is an appendix, and then he talks about representation of this very physical, nice way. Okay, and I just suggest to go and learn that. But eventually, you will find that representation space dimensionality in D dimensions is D over 2 dimensions, smallest representation. So it's in 4 dimensions, 4 over 2, which is 2 dimensions. 5, wait, that doesn't make sense. This probably is even dimension. Oh, that doesn't make sense at all. 5 divided 2 is 1. 2 by 5, very good. And that means 2. Well, something is wrong. So, sorry?
그 플로우가 아니라 더 쓰면은 안 어려워.
Okay, so 3. No, I'm saying something wrong. So forget what I said. You will see something like this. So, okay, anyway, go and check. And A, you not have that. That is related to the fact that there's a reality condition, there's a Weyl representation, there's a Majorana representation. And odd dimension may not accept the Weyl representation, but it can accept the Majorana representation. Something it's related to that. Okay, but you can again approach that question from 2 different ways. A, top down. Okay, I'm a mathematician. I'm just gonna take this algebra. Let me fund it and hammer it. Okay, so again, I suggest to study Polchanski index. Very nice. B, be a detective. Do the detective work. Okay, I don't know. Let me try out and see what happens. Okay, and just try to see and whether you can succeed or not. And you can learn why you may not be able to succeed. Any other question? Let me finish the sentence of what I was trying to say. So towards the end of the last lecture, we talked about 2 projectors, right? And one projector was related to UU bar. Let me drop all the indices. RR, yes, PP, okay? And then we found out that that is related to this. That was completeness relation. This is sum of R, the spin 1, 2 components. Well, I ended up doing everything. Anyway. Then we also found that VB bar was P/-. So this was a one kind of a projector, and more precisely, that either divided by 2m or that divided by minus 2m acted as a projecting a given spinner onto a particle sector or anti-particle sector. So these were the projectors. Another projector I talked about was the thing that I already wrote down here, left versus right, which was 1 either minus or plus gamma 5 over 2. So this time, again, regardless of the representation you're taking, this will project onto either what we call left-handed, right-handed, modulo the correction to be already agreed upon that every plus you see, you should think in terms of minus. Every minus sign you see, you should think in terms of plus sign. We talked about that. So that's the last thing we talked about. And today we will start talking about quantum aspect of it. Okay. Yes.
Since you mentioned higher dimensional quantum matrices, later we will use dimensional regular data. That's my opinion. But then how we can ensure that our gamma matrices are well applicable in other dimensions? For example, 4 minus epsilon dimension with epsilon arbitrary smaller.
Good. So indeed, we will have to go into that. There's a subtlety, and what do I mean by 4 minus epsilon number of gamma matrices? I mean 4 gamma matrices, even then. So even when we do the dimensional regularization, which basic concept is that if you have expressions like, for instance, P for P, and suppose you had a P for somehow, you had to do some integration like this, and then in general, you want to integrate from 0 to infinity, for instance, right? Then this behaves like a P to the 4 over P to the 4, okay? And this is otherwise known as a log of P squared, in case you haven't learned that, okay? Right? So if you had a Px over x like that, so that's a log of s. So therefore, if you send P squared to infinity, this diverges, okay, we have the problem. How do I make this slightly more convergent? Then I say, oh, the reason why this is exactly log, for instance, is because power here is the same as that. Okay, so I cannot change the integrand because this is controlled by dynamics. So what I can imagine of doing that is this. Okay, so now I have a more power in the denominator than the upstairs. Okay, that means that as I send the t to infinity, this converges. Okay, so that's the basics of dimensional regularization that we will do. Okay, I'm not imagining that you already mastered this. So the question was, okay, so it looks like we have to pass on to the some fictitious world where the dimension is 4 minus epsilon. Then if I look at this equation, oh my God, right? So, okay, what do I mean by that? This is a discrete index. So in DMREG, so basically, I mean, we will get to that. We are not gonna change much about this part, okay? We still talk about 4 gamma matrices and gamma 5 as it is, don't touch me, and that's all. So first, and there's a consistent way of dealing with that, okay? And I'm sure in early stage, people tried, oh, gamma 4 minus, no, so that's not gonna work. Okay, another question. All right, good. Now let's talk about the quantum physics. So now we are going to quantize canonical quantization. So Dirac Lagrange. Okay. So what was the Dirac Lagrangian? So we basically constructed the Dirac Lagrangian by saying, okay, I'm going to write down the quadratic action in the field and then single derivative. So we ended up having this expression. Okay, but we haven't fixed the prefactors yet. Okay, so for you, let me just expand a little bit. That means this gamma 0 that, and then so remember this mu, and then there's obviously 0 component, and then that, and this was what we write as Laplacian in the vector sense, right? So that's how we usually write. So that means first let me write. Okay. Good. So then another way of writing this, which is more useful when we now talk about the quantization, is a sigma, so psi bar of that. That was this. This is Dirac adjoint we defined. We did it backward because we wanted to have a simple expression. Now that is therefore psi. Did I say sigma? I meant right. You're all happy with that. Okay. I'm famous for making that sort of mistake. When I'm thinking phi, I'm gonna say 3. I'm gonna think of psi, I'm gonna say sigma. I do all the time, but nobody complains. Looks like it's so convincing. Anyway, you should point it out. This exactly. It's a very and nobody trying to give me motivation to fix my limit. I do it still. So do this and then good so far, and then what happens? Plus I. Now I can write if you want. Doesn't matter. Hold on. No, it doesn't matter. And then minus m sine box. So, I mean, we can write this way, or we can write everything in terms of beta alpha. It doesn't matter. But since we have defined gamma matrices, why not we just write this way? The only reason I wrote this way is now it's useful to derive a canonically conjugate momenta. Because we're gonna. So, what is the canonical conjugation? Remember, canonical conjugation is given a Lagrangian. We want to pass on to the Hamiltonian, right? Good. So once you pass it to the Hamiltonian, so this is a function of generalized coordinate and then momentum, right? And then Hamilton's equation is captured by looking at Poisson bracket of this sort, Poisson bracket of that sort. And then you want to canonically quantize it by imposing this, promoting that to a equal time commutation relation. Okay, so that was the procedure. So we got satisfactory Lagrangian. So therefore, we're going to next pass on to the Hamiltonian. And then we're going to therefore have to find a conjugate momenta to fill the variable. We get this, and then we impose some version of commutation relation. And then checks consistency. So that's what we do. Okay, so therefore this representation is useful because now I can, this right here, I can derive a conjugate momenta. So let's look at the equation of motion. So this equation, and let's derive a conjugate momenta, which is this, by Stowe's definition. And then this equation gives me it should be plus minus I sine tag. Okay, so now let me take the no-brainer attitude. Just proceed. Okay, I'm happy. I don't know if you're happy. I'm not happy, but okay, I'm happy. So let's move on. And are you happy? Anyway, so then, so suppose we pass on to the Hamiltonian, which I will do later. First, let me imagine what am I supposed to do? So naive trial of conjugation. There's naive, which is important. And recall, so for this, let me recall you, okay, we have number scalar, right? So we had a scalar. So for instance, scalar field here we had square, I know we could have written mass, stuff like that. And then we derived a conjugate momenta. And then the argument was the following. So, I mean, it should be the same. That, which you can find to be phi dot, right? Because this has a phi dot square in it. Okay, so then what was the logic important? Well, I know that if I want to do a quantum theory consistent with the special relativity, which we made sure that special relativity is good, because we spent a lot of time thinking about Lorentz invariance, parity, blah, blah, blah. Now it's time to think about the quantum mechanics. Okay? In a way they're consistent with the causality and so on. But here's the time. If I take a slice, temporal slice, now let's look at the light bulb. Okay, here's light bulb. And then the statement was, if given a set of permission operators. So here's a set of permission operators. Suppose here is a one measurement done by OI. Here's another measurement done by OJ. They could be the same, they could be different, doesn't matter, right? So one guy, Alice here, is going to do the experiment here. There's a Bob sitting here trying to do the experiment there. But since they are causally disconnected by construction, okay, so any time slice by definition is a space-like separation as this picture shows, right? That means that whatever this guy does, Alice does, should not be affected by what Bob does and vice versa. And this can be inversed in quantum mechanical sense that, if they commute on space-like separation. So that was the notion of a causality. Okay, that means if OJ does and then OI does and vice versa, they're exactly the same and they're totally statistically, probabilistically, they are independent. Good. So then what we said was that, oh, okay, so let's just first talk about the real or permission scalars first, because that seems like directly related to the observable story. That means that we will have to impose either there is dagger or not. We will have to impose that these are zero if these two points are space-like separated. But the way I have written is already space-like separated, right? Because I'm looking at equal time and then different point. That means I'm here, right? So any equal time commutator relation is the same notion as the fact that I'm imposing causality condition on any space-like separation. So this is called equal time commutator relation. So that's how we start thinking about this sort of process. Okay. So sounds like a cool thing to do. So let's just do it for fermions. So if I do the naive quantization for fermion, therefore, what I will do is the following. Note that we are dealing with a 4-component fermion field, which means that whenever I write down a fermion field, it has a 4 component. 1, 2, 3, 4. Okay? Okay, so again, depending on the representation, either left or right or particle and antiparticle. But anyway, it's 4 component. So therefore, naive trial of quantization, I will do is, okay, let's impose nicely something that looks like nice causality condition. That and then the last condition I have to impose is non-trivial equal time commutation relation between field and its conjugate momentum. So in this case, psi A and the dagger turns out so naively, okay. Let me write this again. So what I will do naively is that this and then conjugate momenta, E of conjugate momenta, which is P, I will impose this. So this should be imposed the delta, including Spinor space as well as the space and time. Okay? So remember, when we first introduced the field, there can be internal degree of freedom and then each of the space and point, we're treating as if for each of the quantum mechanical system, either internal degree of freedom or space-time degree of freedom, we treat them as extra degree of freedom for quantum mechanical point of view. So we promote that to everybody delta function. So that means I'm imposing this. That. Okay, so that might be, what you try. So let's rewrite in terms of that expression. So that means I have psi B dagger. Good, I'm doing well. And then there's a plus minus I cancel I can move up to plus minus here. A, B. Good. So this we might try. Okay. Let's push on and check what could go wrong. Okay, so let's try. Now, let's compute the Hamiltonian. The Hamiltonian is, in general, like sum over conjugate momenta, and then what is this? Dot Lagrange, right? So that's the Hamiltonian. Now since this is plus minus I psi dagger, you can, since you have expression, you can just work it out. So let me just write down the answer, save time. And this is a quick calculation you can do. And because of plus minus I here, there's going to be plus minus I here, and then psi dagger, time derivative of that. Okay? So we should be able to check. So, are you all happy so far? Okay. Good. You're happy. I'm happy. Let me just mention in pass, okay, that naively, this is totally unjustified process. I'm not saying that, okay, there's something wrong about this. I'm saying even more, let me just say in word, and I'll let you figure out if you want to dig in further or not. So what we found is this. So if I look at this conjugate momenta, and from this equation, psi dot, we found dagger. Right? That's what we found. And from the perspective of a Legendre transformation, remember, going from the Lagrange to the Hamiltonian is a Legendre transformation. And then Lagrange is a function of a Q and Q dot, if I just use the Q for generalized coordinate.
네, 쓰면 사라지는 게 많아요.
Yes, so here I use the equations of motion to simplify. So good. So if you do it, then there's time derivative part. There's a there is a spatial derivative. There's a random. But I'm saying if you use equations of motion for field psi, then you should get there. Okay. You might say, why am I supposed to use the equations of motion? Because here I'm taking just classical theory, and obviously all field configuration must have equations of motion. Okay, and then I'm going to quantize. So going back to here, remember Lagrangian once again is a Q and Q functional of Q and Q prime, Q dot. And the Hamiltonian is a function of Q and P, right? The conjugate momenta. So what it means is that given a Q, so let me write the general equation. I'm not keeping my word. I said I'm just gonna say in word, but I'm writing a lot of expression here. So Q given Q dot P, I want to get the function of Q and P. What it means is that this is P. Good. This is one of the variables I want to see here. But that means that I want to be able to write Q dot as a function of Q and P. And the Lagrangian is again Q, which I'm happy to see. But Q dot, I want to be able to write as a Q and P, which means that there should be an inversion process from Q dot to the P, provided the matrix space of a Q and Q dot and the P is invertible matrix. So this is supposed to be providing that information. So given a momenta, I want to see whether given a psi dot, I can convert back into the momenta. But this is not a psi dot, this is psi. Okay? So this momentum information actually does not allow you to invert all the Q dot into a P. Okay? And whenever we have that situation, whenever we have a situation where I don't get invertible matrix between the two, it signals the fact that the system you're dealing with is a constrained system. And you have to sort it out. What kind of constraint you have, how to deal with that. Okay, there's a general process. Some people like it, some people really don't like it, some people find it useful, some people find it totally waste of time. It's up to you. I mentioned to you. So there are names to this. Okay, so this type of constraint you get is called the primary constraint, because you get from the first path of the equation. By imposing consistency on this first level of equation, you get the secondary constraint. And then you collect a whole bunch of constraints, primary, secondary, and third, fourth, blah, blah. And then you check the properties of constraint. You look at the commutator of the two constraints. If they either vanish or not, depending on that, you say first class versus second class constraint. And anyway, and then there's a way of dealing with that. Okay? And Dirac system has second class constraint, just the final result. But since you were all happy, we drop all of that. Why is it okay to drop all of that? Well, if you just go no brainer, the final answer is good. Okay. But if you want to learn how intermediate step works out, and why that's the useful thing to know, you can go and check one of the chapter on Weinberg. Maybe it's chapter 7. Okay.
Doesn't the non-invertibility of the constraint signal something like gauge something?
Good. So, like I said, non-invertibility comes from this fact. So it gives you some sort of constraint.
Yes.
Okay. Then I told you that based on the way constraints are born, meaning this is born at the first stage of a process. It's called the primary. And then there's another constraint possibly can be born at the second stage of a checking consistency of the constraint, called the secondary constraint. But then, depending on the property of the constraint, meaning you don't collect the entire constraint, and then there's a closed set system of a constraint, you can check the properties of that by looking at the Poisson bracket property. Then I told you that there's two different kinds of constraint. One is first class, the other is the second class. First class, I think commutator of Poisson bracket all vanishes. The second class, they don't vanish or something like that. So first class constraint is gauge redundancy. Second class constraint is actual physical constraint, meaning just like putting the ball on the sphere of the sphere. That's like actual physical constraint. And Dirac system doesn't have a gauge redundancy sort of constraint, but it has a physical constraint. So I told you that it has a second class constraint, not the first class. In principle, one can talk about the gauge theory too, but we are not going to do that. Okay? But if you like to spend and you have a lot of time to waste, go and learn. It's useful to know. I mean, you never know whether it will give you clarification of some of the subtlety you encounter during the research. So it's good to know, at least, that such a thing exists. Okay, a lot of digression. Let's move on.
디렉터리 중에 저렇게 나오는 거 제가 생각 없이 그냥 되게 많은 건데.
Yes.
지금 중간 과정은 아픈 거고.
Yes.
그럼 혹시 저거를 돌파하는 게 그냥 맛보기로 스킨만 하자.
That's a whole different lecture, probably 2 lectures. Maybe, I don't know if it's 1 lecture, it's sometimes. Yeah. So it's such a, okay. So yes, that's what I just mentioned in Word with a couple of equations. But okay, in Word again, you collect the system. Okay, and then you split into first and second class constraint. Second class constraint means that there's a constraint equation, and then if you look at the Poisson bracket, there's non-zero commutators. Okay. Then entire phase space is not acceptable. So you have to constrain to actually linearly independent phase space, Q and P. And some of the P and Q are not all linearly independent, so you have to know how to drop those as part of the phase space. Okay? And then technically, the way you can achieve that is instead of Poisson bracket, you have to define a new sort of bracket that achieves this job called the Dirac bracket. Okay? It's a horrendous expression sometimes. Anyway, so instead of nice, Poisson bracket, which is, Q over Q dot, the derivative, blah. You have to design a new bracket called the Dirac bracket. Now this says all happy nice property, meaning now you successfully constrain to only the independent, the physical parameter space or the phase space. So now you have a Dirac bracket, and then you now promote that Dirac bracket to a commutator. But that is the quantization process. Yes. You can say what happened if you have a first class constraint. Okay, I should really have to stop. I never prepared for this. If you have a first class constraint, then there's a way of converting first class constraint into the second class constraint. Okay, this is where this mysterious word coming that the gauge redundancy hits twice, meaning if you have a one gauge redundancy, it reduces degree of freedom by 2 instead of 1, because a single first class constraint eventually turns into 2 second class constraint. And then you Poisson bracket, go to the Dirac, and then you condense. Okay. Again, if you have time to waste, do it. I had when I was first in a little bit. Let's move on. That was good. So then we are here. All right, we are here. And then so forget everything I said in the last 10 minutes, please. Okay, so what we done was that we start out with the Lagrangian. We say, oh, looks like causality, so that means I can impose this condition, right? Do it. Now, one thing that I want you to keep track of is that, so let me actually just erase it so that you actually don't even bother to think about it at all, okay? So then what happens is that there's this plus and minus sign, and then remember this plus minus sign ambiguity came from the fact that original Lagrangian had a plus minus sign ambiguity. Okay, so whenever you see plus minus sign in the next 10 minutes or so, that's exactly the plus minus sign that we did not fix when I wrote down a Dirac Lagrangian. Okay, good. I lost much here. All right, so then what you gonna do? Let's keep moving. What you gonna do? And then we talked about plane wave solutions. Okay, so we talked about plane wave solutions already, and we studied them. So for scalar case, let me just parallelize it so that in the scalar case, we constructed a scalar field by saying that I'm talking about a real scalar field. So this was an expression that we had for scalar field. How we did that? Well, we said that, simplest way to think about it is that, I had a Klein-Gordon equation. And then I looked at the two plane wave solutions. One is a positive frequency, the other is negative frequency solutions. So I write down a linear combination of the two. Okay? But then everything was in the momentum space before that, other than this plane wave factor. Okay, momentum space picture was useful when we talk about the construction of a Fock space, right? Because there's a momentum, I can say P or multi-particle state Pn, and looks like it's useful to think about the momentum space. But if we want to have a clear way of imposing causality, which is about the space-time picture, somehow we had to know how to go from the momentum space to the space-time picture. That's where we said, maybe it's useful to introduce a field, which is a function of x instead of a p. Okay, and therefore this expression is nothing but all linear combination of a positive frequency plane wave solution, negative frequency plane wave solution, and then passing on to a space and time, assuming this is a linear combination of creation of knowledge and operator back then. And then we imposed causality conditions to figure out what the coefficient needs to be. Okay, so that's how we built up. Okay, so we're gonna not do the same thing. Okay, so therefore, we're going to talk about the plane wave solution, and then promote that for fermion, promote that to a sort of a field, and then check properties whether that's sensible. Okay, so that's the step that we're gonna. Okay, so let's proceed. So here is my fermion field. You write and count components. So I'm up to this prefactor, which you may not find a very happy expression, but you will see that's sensible soon. We found the two plane wave solutions. One was UOP of R. So we had a plane wave solution. One was U of ER with e to the minus IP minus. Okay? Unlike the scalar case where plane wave solution was just that, right? Single degree of freedom. We're talking about now fermionic representation, especially for component object. So plane wave solution already had this, four component column map. Okay? So this is still part of the classical solution if you like. And then there's a prefactor when I superimpose positive and negative frequency, and that coefficient, right? We promote it to the operator. So for this, we're going to introduce a coefficient, which I called it B, and then R. And then we had a negative frequency solution, which with the coefficient function B, it's the pulse I theta S, imposing coefficient condition. And then we're going to introduce a coefficient, which is the COP, so then R. And then we say a dagger, because I want to have a combination of alpha dagger, similar here. You can ask why that combination was needed. Again, that was somewhat deeply related to the causality. So this is an ansatz, okay? So far, I just writing down this. So, and then you can, again, immediately write down a conjugate of that, or conjugate momenta, because conjugate momenta is a psi dagger. So I should be able to write down that thing here too. Because we're going to use this expression to compute several things from now. Actually, let me bother to write down that expression. Let's see if we can do that quickly together. So I'm going to basically take a conjugation of that. If I do that, so conjugation of that is dagger, U dagger, R dagger, E, is the plus I theta S. Minus theta S. Good. Okay, so let me make a couple of comments at this point. Are you with me? Am I alone? Are you with me? No? Okay. So, yes or no? Right? So, yeah, because I had a 1 and 2 and 1 and 2, right? So I just writing up there. Now, okay, for comment number 1 about the measure part, okay, that doesn't look very happy compared to that. First of all, recall that this combination right here was a Lorentz invariant phase space integration. Okay, good. Now that thing doesn't look at all like happy Lorentz invariant integration, but you may recall that there is a convention that you can pick. For instance, if I pick A, creation operator AP acting on the P as my single particle state, you can check that in this thing where A dagger satisfies just delta function normalization. And this thing also is just normalized as this. Then because of that fact, meaning Lorentz invariant measure has a 2p factor, E2E factor, this is not Lorentz invariant delta function. Okay, in fact, if you want a Lorentz invariant normalization, that thing is actually 2e times delta. I'm just reminding you all of that, okay? On top of that, if you also care about the where to put 2 pi's, for instance, we can pick this as our normalization. So then, in order to get to that point, I define or define another creation operator or annihilation operator, which is related to the conventional version, but only related by rescaling of this factor. Okay, so here I have written things in terms of this Lorentz invariant normalized guy, alpha alpha dagger. That's why you see Lorentz invariant normalization. Now, if you plug in this rescaling to that, you see that exactly you will get 2 pi to the 3 halves square root of 2e compared to that. So that's all that. So basically, that means that these later operators will satisfy not the Lorentz invariant, thing, but this more conventional commutators. Okay, so that's why. Now, now we're gonna have to sort it out this. So let me actually erase this part and then continue. Good. So either way, now starting out with this, and then if I promote this to the operators, which means that I'm imposing now quantum mechanical equal time commutation relations, you can ask, how can I satisfy these relations? That means that what kind of commutator should I impose on these latter operators to be able to get there? And if you look at these first two, these two can be very quickly satisfied if you impose B, dropping all unnecessary expressions. BV equal to 0, B dagger equal to 0. And similarly, CC equal to 0, C dagger equal to 0. And all the BCs are equal to 0. Either there's a J or it doesn't. Then immediately, this is true. Let's check. So if I look at the psi with the psi, right? The only commutator I have is a B with the B with the C dagger with the C dagger with the B, right? That's all I have. So if I impose these conditions, it's clearly 0. And similarly for psi dagger. But now, therefore, the only non-trivial thing we have to check is psi with the psi dagger. Okay? So just like from the scalar case, we had an intuition. So if I have a layer operator, now let me write slightly more carefully. S dagger, so it's as if I have alpha alpha dagger. So suppose I impose some non-trivial commutators. So for that, let me put an ansatz following Coleman. And then I won't impose orthogonality, so RS, and then P minus Q. And likewise, let me impose CPR, CQ, S dagger. And then likewise, I can impose this delta RS, rate minus Q. Okay, so that's right. And then our job is to fix B and C to see if we can satisfy this condition. Okay? So, I mean, now you can just do the computation because now you're looking at commutator between these two. So you're going to have BB dagger, that's non-trivial, so you have a UU dagger, right? It's an exponential combined. And then C dagger C, BB dagger with exponential combined, the cross term vanishes. Good? So overall, what you're going to get is that you have a single measure because BB dagger will give you a delta function. So starting out with a 2 momentum integration, 1 just goes away if you use delta function, right? So what you're going to get is that basically BB dagger, UU dagger with exponential. And C dagger C, BB dagger with exponential. Now, therefore, you see that from the structure, it looks like slightly more more useful to actually write an expression for C dagger C rather than CC dagger. So if you look at the Coleman, actually, he writes out dagger here and then that expression. Okay, totally conventional for now, right? Because if I know this, the other one is minus half of that. So who cares? Good. So without actually going through the calculation, which now you should be able to do it almost, okay? You will see that you can satisfy this commutation relation. Basically, I'm showing how to do that. And then when you have a UU dagger, you might say, oh, I'm panicked. Now I'm doomed. But I wrote down already projection operators. UU dagger sum over R is P slash plus M. And then similarly, BB bar is P slash minus M. I told you. Okay? So that means that when you have a UU dagger, you can turn this into the UU dagger instead of UU bar by multiplying gamma 0 here, right? Same thing here for. You can compute it. You will find out that, for this condition, with a single change of moment integration variable, which you will see that this can be satisfied if V of P prefactor is same as C of minus P prefactor. Because when you do that, you may have to do a change of variable from P to minus P, so that this looks more easy. And then this can be now anything, either plus or minus 1. So then that can be satisfied. Once again, plus minus is exactly plus minus ambiguity that was sitting in the left so far. Okay, good. So it looks like we can do it. Cool. So let's do it. Looks like so far we don't have any problem. But there's a problem on this thing. So what is that problem? So that problem is good. So now you have to check. So then we can quantize it. Now let's actually compute the Hamiltonian. So now you can compute the Hamiltonian. This literally. So now you have these operators with the commutation relations cleared up, and you have all the explicit expressions. And then these prefactors are almost fixed to this. So now if you compute the Hamiltonian density or Hamiltonian, you get the following expression. So I just want to save a space. So forgive me to write down everything in slightly compact, right? So H, the total Hamiltonian, which is space integration of Hamiltonian density, right? So then if you compute this, now by plugging literally that into that and using commutation relations, you get plus minus. That's again exactly the ambiguity coming from the overall factor. Entropy, good. Energy, good. And then you want to see number operators, right? So you see the number operators, and you get BP there is a sum over mode, SP mode. Dagger BP minus CPR dagger. This is the expression you get if you compute the Hamiltonian. So that looks almost good because energy should be obviously, for each P mode, I have that energy. The question is, how many number of them do I have? And then I want to sum over entire excited mode. So not only momentum excitation, but also spin excitation. I'm summing over. And remember, what was the B and C? So this was, if you remember, a particle profile, right? This was a antiparticle. Because this is positive frequency mode, this is negative frequency mode. What that means is that this quantum field it can annihilate a particle and it can create an antiparticle. What it means is that B dagger B will count the number of excited particle. And on the other hand, the C dagger C, which this is not quite there yet, will count the number of antiparticle excitations. So you might say, oh, okay, this may be fixed if I actually rewrite this in terms of C dagger C. Okay, so let's do it. How can I write this? Well, I have a C dagger, and then since I impose commutators, I'm going to write C dagger C plus C dagger C. Remember, the only reason I put minus sign here there is because I imposed commutator so far. Okay, so that's commutator. And this will be C dagger. That will be some delta function, especially since I'm looking at R equal to the same, P the same. This is just like delta of 0, so infinity. So overall, the structure is plus minus, once again, the ambiguity. So energy of each mode, excited mode, the B dagger B, good. But then, because of the commutator, what I get is a plus C dagger C, and then with that minus, I still get minus C dagger C. And then there's overall infinity, which I don't care for. Okay? So Hamiltonian has a quantum excitation part, and then this divergence. Once again, we can take care of that in a meaningful way, so we don't have to worry. So this is the expression you get as a consequence of quantizing with the commutator. So everything good? Everything good? Cool. Is everything good? No. Right? No. So what we want is the Hamiltonian is bounded from below something. Okay, right? And I told you why. We are about the quantized theory. And then if Hamiltonian is bounded from below, and suppose I start out my theory here, and then I talk about small excitations on top of that, so fluctuations, those are particles, or mode, or quanta, whatever you want to say. And then it makes sense to talk about the perturbation theory, right? Starting out with this, small excitations, you will never widely go off. But if Hamiltonian is not bounded from below like so, then say I want to start out quantum field theory here. And then if I turn on the small excitations, this guy say, wow, here is much better than that place. Let me leave the room and never come back. So it just wildly destabilize the system. So in this sense, there's no sense of quantization with respect to classical theory when I talk about small fluctuations, because there's instability in the system. So this thing fails to satisfy the criteria, because no matter what you do with the particle, there's always this antiparticle excitation you can pick to destabilize, or vice versa if you pick the minus sign here. So this Hamiltonian is not bounded from below, and quantization failed. So what do we do? So in order to rectify this problem, we have to do the following. So it's quick, and then we will learn why that's the right thing to do also. So we're talking about the fermionic field. So these are all fermionic fields. So instead of the commutator, as you'd expect, now we have to use anti-commutator. So let me actually write more general code. So if you have a set of, so in your QFT or quantum theory, suppose you have a bosonic variables, which let me write it as a Q and P. And then you also have a fermionic degree of freedom, which let me write as a theta for the generalized coordinate, and then pi for the conjugate momentum. Then when you pass on to the quantization, then for bosonic coordinate, you impose all the commutator, equal-time commutator relation. For all the fermionic coordinate, you have to impose, on the other hand, anti-commutator, pi. Yeah. And then for mixed commutator, you impose commutator, either p here, either pi here. So that's what you do. Okay? And I'll justify momentarily why this is the right thing to do. Also, in addition to curing this problem that we just discovered. So let's replace what we have done so far. So instead of a commutator here and here, now we're going to impose anti-commutator. Okay. So what we're going to do is first see that this actually has a way of solving this problem first. Okay? And then I will also argue why this is also the right thing to do for fermionic system. But so far, Any questions? Okay, good. So now, we're gonna do this. You might say, oh shit, we have to do the computation all over again. No, the structure is exactly the same. If I look at the commutator, now I need to look at the anti-commutator, right? Same. So instead of looking at the B dagger commutator, I just need to look at B dagger anti-commutator, so I just use that relationship, right? Other than that, prefactors plays out exactly the same. So all the computation basically the same, except the fact that whenever you had a B dagger or B, C, and so on, and the first commutator, you replace that with the anti-commutator. That's all the replacement you have to do. Otherwise, it's identical computation. So basically, the entire expression can be recycled. Good. So, so then if you repeat this computation with that, when you try to do this condition, you again will find out that you have to do this so far. Exact same argument. Not even a single thing has changed. So when you try to impose, so now, okay, oh, a lot more. You see? Okay, I'm debating. This is mapped onto this. This is mapped onto that. So everything now works out. Okay, good. Then if you, so now these two are trivially satisfied, right? Because there's as we said, B, B, C, C. And now for the last one, the only non-trivial commutation relations, you will find that this still should be satisfied. Previously, there was this ambiguity, which the ambiguity is exactly the same as that. So there's a two way of seeing which one is correct. First, now if you compute the Hamiltonian with that, now you will find out that instead of a minus, so up to this point, you will get the same answer. But at this point, now since I know that I have to impose a anti-commutator, that means I have to do this. That means that I will have a minus. That means that with the minus sign combined, I will have a plus sign here. Okay? Good. So now if you look at this, yeah, it's obviously clear that I have to be plus sign here. Good. And then there's a second way of seeing that. Let's see. Good to go. You're almost cleared up. Second way of seeing is the following, which is good to know. Suppose I had a fermionic operator. So if I had a fermionic operator that satisfies anti-commutator relations. Suppose let me just write it as a super dumb way 1. Okay? So in more realistically, what I mean by this is this. So now I'm going to impose Q dagger is delta, well, I didn't write RS, delta 3 T minus Q. So I just rewrite this as this very simple expression. Now for any state, for any given state phi, I get sandwiching this theta dagger to phi. I can write this two different ways. So one, what that means is that since that's 1, that will give me phi, which should be positive. But then suppose instead of that, suppose I say, oh, I don't know which one I have to impose. Let me just allow plus minus 1. In this case, if I do path onto this, I get plus minus this. So I don't know what to do yet, because that's the first path. Second path, I literally use the definition of anti-commutators. That's the second path I do. So phi theta bar plus theta dagger theta phi. Very good. So then that is equal to, the first thing is the square of that piece. So theta dagger acting on phi to the epsilon square. And the second piece is again now theta acting on the phi to the epsilon square. Right? So this one is manifestly equal to greater than 0. And this therefore have to be equal to greater than 0, which means that I have to pick both sides. Checks out. So what I'm trying to say here, So two things. Yes, we impose anti-commutation relations. And then just satisfying this anti-commutation relation for quantum field in terms of creation of knowledge operators does not yet tell me exactly which one I have to pick yet. I'm saying there's two ways of fixing it. A, just look at the Hamiltonian and make sure that it's bounded from below. Okay. However, I'm saying there's a more generic argument for any fermionic, anti-commutation relations. If you had a sign ambiguity, by just going through this argument and acting on the arbitrary state, I'm saying the coefficient should be positive. Yeah. Or standard. Okay? Good.
Then do you mean that the plus sign is required to make the Hilbert space really defined? I mean, for Hilbert space, the norm must be positive.
That's right. That's exactly right. Yes. So otherwise, you have to somehow say that, oh, you know what? I have a ghost, right? Like I have a negative norm state. Ha ha ha. So if you don't want to do that, then yes, that's what I'm saying. Yeah, and such thing does appear, by the way.
Yes.
In some of the quantization of Coulter-Floyler quantization of alternate. Anyway, sometimes it does appear. And okay, so where are we now? Yes.
The equation of motion for the Fermi case, then they use the anti-commutator instead of the commutator using the Hamiltonian.
Yes. Let me. Oh, you mean the Hamilton's equation?
Yeah.
Yes. So good. So then, more precisely, given Hamiltonian, then suppose we pass on to the quantum state, the quantum field theory, where we have a meaningful motion to talk about, moment to talk about commutator versus anti-commutator. Then Heisenberg equations motion will be in terms of anti-commutator rather than commutator, if that was your question. Okay.
I have one more question.
Yes.
So we have chosen the Dirac bracket to pass over from.
Oh no, sorry.
Yeah.
No, can I rectify this first?
Okay, yeah.
Because I absolutely lied to you. Maximal way. So, and then I come back to you. So hold that question. Okay. Hold on to that question. Yes. So, did I read? Yes. Okay. There's a random of it. We impose an anti-commutator for fermion. And I told you that if you have a bosonic and then fermionic, then you impose commutator. Okay. Now, Hamilton's equation has a structure that change of something is a Hamiltonian acting on that field, something like that. And Hamiltonian is always quadratic in field, or fermion field. And so this is the bosonic operator. So it is actually a commutator that you have to use. Okay? Okay. Good?
Then what if no, okay.
Okay. But do you understand what I'm saying?
Yeah.
And then I'll give you one example of this sort of calculation right now, basically.
Yeah, I wonder that if Hamiltonian has all some of the
fermionic operators in it.
Yes.
Good. I will also answer that question, sir.
Okay.
The answer, you're not allowed to do. Yes.
So we pass on from the Clausen brackets to Dirac brackets, which is where Dirac brackets was the commutator.
Dirac bracket. Okay, now you're there now. Okay.
Okay, so then you have to swap that to anti-commutator. So is it okay to do that?
There is a consistent quantization condition if you want to follow them.
So that's just subtle way, but you're basically allowed to do that?
It's not allowed to do that. You have to do that. Okay. A, yes, you're allowed to do that. B, you're not allowed to do the other way around. So this is what now. Okay, so now let me give you another reason why anti-commutator is a consistent thing. I mean, looks like we talked about a lot of things, but to summarize, starting out with a Dirac like Bryan Gin, we tried out the knife thing with a commutator. And commutation relation seems to be possible to saturate by imposing proper commutation relation on the B and C's. The problem occurred by looking at the Hamiltonian that cannot be bounded from below. So we had a trouble, right? And then, therefore, we rectify by imposing anti-commutator on fermion field rather than commutator. Looks like we can do it. But there's another intrinsic problem with the commutator rather than anti-commutator for fermion field. So I'm going to discuss that. So in other words, this is not the only problem. There's one more if you actually use a commutator. Okay, so what is that problem? So next thing I want to talk about is Fermi statistics. Fermi statistics. I'm excluding this all. Okay, so suppose I have a two-particle system. I mean, we can talk about many particle system, but the argument will be exactly the same. So suppose we talk about two-particle system. So in the first case, I'm going to talk about the bosonic two-particle system, which I write it as P1, P2 state B. Okay, B means boson. And by now, I don't have to, I guess, explain to you that this really means that 3 vector P, because if I impose on shell, only 3 independent degrees. Okay, we all know that. And then for boson, we know that it should be plus P2, P1 if I exchange the 2 states. Okay, and then we can write down exactly the same thing here. See if this is enough space. So now let's also talk about the fermionic two-particle system, and I'm going to write the same way. So P1, P2, F. And I know that this should be minus of P1 plus P2, P1 of F. So now you can say, okay, let me write down the bosonic state as alpha P acting on this as my bosonic state. And then here, let me write it as not beta, which is tempting, but B, because I already used B, and P, totally different notation. Nevertheless, it's fine. So P of a fermion system. Okay? Very good. Checks out. I was expecting.
I think both should come with dagger.
Very good. I was expecting that too. So you see, I'm giving you a lot of this today. Make sure you're keeping. So now let's actually check this. Okay, so that means that I can write this as a alpha P1 dagger, alpha P2 dagger acting on the vacuum. So that's one side of it. The other side of it, alpha P2 dagger, alpha P1 dagger acting on this. So then the statement of Bosch statistics means that these should be identified. Right? So therefore, even from this, you discover that the consistent algebraic structure you need to impose on these ladder operators for bosonic system is actually dagger Q is 0 or non-zero if you look at the alpha dagger, but that's the same thing. Okay, and now you expect the same thing here. So now B1 dagger, B2 dagger, probably already see immediately. B2 dagger, B1 dagger acting on the vacuum. So by demanding that this should be now minus of that, so you immediately see that the correct algebraic structure to impose or without a dagger doesn't matter. It's anti-commutator. So what that means is that in addition to Hamiltonian being ill-defined and so on and so forth, just intrinsically, if you want to talk about the fermionic system, this is the right thing to do. And then you can immediately discover Pauli exclusion principle. Otherwise, it will not even satisfy that. Now let's talk about identical particles. Identical two fermion particles, which means that in this case, I'm just imposing P1, P2. I'm assuming that this state that has had same spin state. So I'm just dropping that extra degree of freedom part. So by demanding same momentum, I'm already assuming that they have the exactly same quantum number. And this P1, P2, P1, P2 immediately shows that P1, P1 identical state fermions should be zero, meaning such a state cannot exist in the Hilbert space. And that is nothing but exclusion principle. And once again, exclusion principle can be realized successfully if you impose anti-commutator rather than a commutator. Because that just means algebraically that B squared, if I look at the exact same object, is zero. So that just means I cannot create twice the same thing. Okay? There. What's that? Dagger. Cool. Anything else?
Professor,
Yes.
I have one question.
Yes.
So then does the bosonic and fermi particles arise from the same vacuum?
Oh. Yeah, so vacuum they can come from the same vacuum of quantum field theory. So okay, let me give. No, I'm not going to be.
Okay, yeah.
At least let me give an answer. Given a quantum field theory, so suppose somebody hand you a quantum field theory, then the first thing, probably not the first thing, but at least one of the things you want to understand is that what is the vacuum structure. Sometimes you are given a quantum field theory that has a trivial single vacuum. And then on top of that single trivial vacuum, every excitation is like a particles that allowed by that field theory. Sometimes quantum field theory has a more complicated and interesting vacuum structure. There's a one sort of vacuum, another sort of vacuum, many different kinds of vacuum, or connected or disconnected, like many different kinds of things. Depending on which vacuum sector you are in, you might be talking about slightly different excitations, a lot you talk about. Okay? But here I'm assuming that there's a single unique vacuum O that I write down, and then everything is defined with respect to that vacuum. And then I'm going to excite the excitations, those are my particles. But again, quantum field theory sometimes enjoy very rich, interesting vacuum structure. Sometimes that's the golden $1 million questions. And there's actually genuinely $1 million question about the vacuum exists. No one has combined.
Then is there something like a bosonic vacuum or fermi vacuum, something like that?
Good. So in principle, yes. So in principle, you're asking whether the vacuum state satisfies Bosch property or fermionic property. In principle, conceptually, you can talk about fermionic vacuum. But clearly, fermionic vacuum doesn't respect the Lorentz invariance. Why is that? Fermionic vacuum means it's a spin state. Vacuum has a spin state, right? And then if you add the Lorentz rotation, they flip. So vacuum doesn't respect the Lorentz invariance. We call symmetry being not respected by vacuum to be spontaneous symmetry breaking. So if you want to talk about fermionic vacuum, that means that that system doesn't fully respect entire Lorentz invariance. Some of them is broken. But that's possible. Some of the condensed matter system might have that problem. I don't know. Okay. Okay, so interesting. So that clock is correct clock. Can we double check?
It's correct.
Yes. Okay, good. Good. Looks like I don't have to prepare that hard. Okay, so then let me mention today I have to run out pretty quickly after 4. So here's the option. Do you have a question you want to ask? So I can spend 7 minutes here and address questions. Or do you want to hear a little bit more and then I disappear? Okay, let's first address question and then.
이전까지 모든 과정 중에 사실 오른직면하게 해서 그 스미스를 쌓았는데
네.
여기서 사실 이게 지금 여기서 이제 페르미온일 때는 이거 만족해서 와이프 커뮤니케이터가 결과물을 느끼는 거예요.
네.
만약에 지금 저희 이전 과정 중에 제가 프로서스한테 라그랑지안이 페르미온이라는 물건을 어디서 구할지?
Okay, let me understand. So, in which part of the construction do we know that we constructed the theory of fermion? Is that your question?
페르미온인지 아닌지 저희가 주장할 수 있는 근거.
Good. So the question is, yes, we wrote down Lorentz invariant Lagrangian that had this psi bar psi and then some derivative master. In which part of the construction we knew that we are constructing theory of a fermion spin half fermion, spin half particle. if the question was, in which part of the construction did we know that we were constructing spin-half particle? There's a sharp answer. If your question is which part of the construction of Lagrangian, we knew that we were constructing, this, not the spin-half, but fermionic Lagrangian. That is a slightly different question. So there's a spin question of spin, so spin-half. Because we constructed, we start out by saying that what is the minimum representation of Lorentz group, which is either half zero or zero half. And then let me understand the representations. I introduced the two component spinner, rotating under this, and then I put them together to construct the four component spinner, and then I try to construct a Lorentz invariant object out of that. So it's clear that the Lagrangian we constructed certainly describes a spin-half particle. What was not clear was, which part of that construction told me that this actually should be a fermion of this kind. So maybe there are multiple ways of attacking it. So if that is the question, that's a great question. So that's a great question. Good. One way to do that is taking a more axiomatic approach. Like, okay, I know that by spin statistics theorem, which is one of the math theorem, that any spin-odd state are necessarily fermionic. Any spin integer spin state must be necessarily bosonic state. Since I constructed spin-half, I know it should be fermion. Therefore, let's impose that at the quantum mechanical level. So this means that you have to just buy and believe without knowing why that's the case. Or you can view today's discussion as a part of extracting that information. Suppose I didn't know that, yes, this is spin-half particle, but I don't know it's fermion or boson. Let's proceed. And then if we just run it, and then commutator, good. Oh, Hamiltonian is not well defined. Looks like I can fix that if I impose anti-commutator. Okay? But then, okay, what does that mean that I have to impose anti-commutator? But then you can just follow this argument. Oh, that means that whatever I constructed must be fermion. So in that sense, you can view this as a sort of discovering spin statistics problem. Good. Yes, 3 minutes. Yes.
근데 좀 맨날 헷갈리는 부분인데 이게 결국 암시하는 게 페르노니 필드가 그라스마니안이라는 거잖아요. 근데 여기서
Yes.
컨주게이트 모멘텀 정의할 때 데리베이션 하면
Yes.
제가 뭐 레프트 데리베이션이랑 라이트 데리베이션 막 이런 걸 봤거든요.
Yeah.
그거에 따라서 뭔가 사인이 달라지잖아요.
Yes.
혹시 그거 정하는 게 컨벤션인가요? 아니면 뭔가 룰이 있나요?
Good. So yes. So good. One thing that I was gonna say, which we probably have to start next time, is that yes. So what he's saying is, this means that if I take a classical limit, for instance, what do I mean by that? So here is a commutator, right? And you know that all commutator has a secretly like H bar hiding. Okay. So let me say that again. So for instance, if there's a Q, P, I, H bar. So that's the actual commutator relation, right? Now, if I restore H bar, which is 1, so that's why it already found. So in the case of fermion, you will have something like this. So then if I take a classical limit, whereby taking H bar goes to 0, that means that classically I have a Q variable, P variable, which I don't have to worry about order of it. Right? So it's called the C number, commuting number. But then if I take the classical limit of this fermionic system, even classically it looks like I should be careful with the order of it, for instance. I mean, this is also true for all other commutators of this. So then we say that this is the C number variable. We call this sort of a variable. Now I'm talking about this variable, classical physics, okay? It's called the Grassmannian. Grassmannian variable. Okay, there is a 30% chance I might be putting wrong number of n's and s's, but something like that. Okay, so some deformation class of this thing is the right thing. So Grassmannian variable. And you can say, oh, I never heard of Grassmannian classical mechanics. Looks like we have to learn it, right? So what if I want to talk about the classical mechanics of a fermion? Looks like this is the right thing to use, but I never learned that. Because you didn't learn that, that doesn't mean that that doesn't exist. Indeed, that exists. Grassmannian classical mechanics exist. And I learned it once. Not because I had so much time to waste, but the professor who taught me quantum field the first time spent like 2 months on corresponding classical mathematics. It was like, oh, minus sign, minus sign. I have a 50% chance I got the wrong answer. So yes, the answer is therefore, in order to Jesus, xi, xj, I know what to do, xij, right, delta ij. But now, if you want to do it, depending on the chain of writings, j, k, and then if I do the derivative of that thing, so that was the question. Okay, L. Oh my God. So then, yes, so yeah, there's a convention one have to pick. And that sort of convention is the same convention as you would encounter section 2 of supersymmetry the framework, for instance, like which minus sign. So, I mean, the convention is that you have only act on the guy that sits right next. And then if you want to echo that guy, what would you do? Well, you have to first split and then act. And so on. Integration is exactly the same. So it's the Grassmann integration. So this is one you probably have heard. 1 is 0, and so on. R is 0, and so on. So there's a set of rules for Grassmann derivative, the Grassmann integral, and then perhaps you have heard that Grassmann integral is identical to the Grassmann derivative. And so on. So we will go through this. But did I address your question, or just mumbled over?
I'm not satisfactory about
Okay.
the time.
Okay, so the answer is, well, my answer depends on what was the question.
그래서 FX 데리베이션이랑 라이트 데리베이션 있잖아요. 그거 가지고 컨주게이트 보면 좀 정할 때 이게 디멘션인가 아니면 뭐 그걸 정의하는 게 뭐 그런 게 있다.
Hey, there is a convention one has to pick to define a derivative. Once you pick a convention for the derivative, then you can define derivative including anti-commutator including derivatives and so on and so forth. So at that point, if you remember a form of Hamilton's equation, which is the commutator of derivative and so on and so forth, then once you pick a convention and definition, then you can do it. But this is the least recommendation for me to learn that. I mean, you will learn the Grassmannian calculus soon to deal with quantization and so on and so forth. But what I'm saying is, I don't think you need to spend any single seconds on the Grassmannian classical mechanics. I absolutely didn't get anything out of it. Okay, is this recording?
I'm afraid I was wondering about the question.
Okay, so in general, it is good to learn whatever, but no, I absolutely don't know anything about it. Yes, is it recording? I guess so. But I don't know. Probably I said a lot of bad things already right now. It's too late. Okay, so that's it for today. If there's an urgent question, I'm happy to spend 2 more minutes. Are we all? Good. We are all.